Right, so here for the week 8 for the mid-semester exam, I add this one, the exam one explained, the one that Pak Udin explained on Wednesday. So you can have a look here, just to make sure that if maybe some of you or one of you didn't pass the test, then need to get the remedial, you can maybe study more about this one. Okay, and then for now in the week 9, here we will learn about equation of change in non-isothermal system. I uploaded two handouts. The first one is that what we're gonna discuss for today. The second one is I got it from Pak Mubiar almarhum regarding more comprehensive of that. So if you're interested, and there should be some application as well, I might want to explain a little bit about this, especially it will have a lot of application. Okay, so here we're gonna talk about the equation of change with this slide. Okay, and I think I would like to add for week 10, let me write it here. Pak Anggit will explain to you about flex PDA. The thing is, because usually in more complex heat transfer or heat transport and using equation of change for a non-isothermal system, it's very difficult for us to do just only a manual basis. Okay, so that's why Pak Anggit will explain about the basics of flex PDA and how you can apply that into the software to get some result about equation of change and so on. Okay, so there you go. So we're almost now we're week 9 here. So week 10 is flex PDA. Okay, so let's have a look. Okay. Alright, so now we're actually would revert to chapter 10 in BERT, so you may want to see that one there. Okay, so maybe the first one, let's just review what does it mean with energy balance. Okay, in energy balance, we know that the rate of increasing kinetic and internal energy, that would be equal to the net rate of kinetic and internal energy addition by convective transport. Okay, and then the net rate of heat addition by molecular transport, which is a conduction, okay, with the convection and the conduction, and then a rate of work done on system by molecular mechanism, for example stress or shear stress or viscosity, something like that, and rate of work done by external forces, okay, for example by gravity. Okay, so in similar with equation of change for molecular transport, we can actually build the equation by assuming first like a box, like a control volume with a delta of this one is a delta x, and also the height is delta z, and the width is delta y, okay, in the Cartesian coordinate. Okay, so we assume that there would be a heat flow from to the x positive, yeah, to the that there, and then to the z positive, and also to the y positive. Yeah, so let's try that one. Okay, where this is the x positive, this is the z positive, and this is the y positive. Okay, so so if you want to calculate, we have to calculate the heat per volume, heat rate per volume. Okay, the heat rate for volume is actually defined by the kinetic energy, and the kinetic energy half mv square. Yeah, so maybe I can write it using. Okay, so so this one is kinetic energy. Okay, because if you remember, this is half mv square, but it is divided by the volume, so it become rho. Okay, and this one is also internal energy. Yeah, and the internal energy, this is again mu, the mass multiplied with the heat, the internal energy, the unit for the internal energy, but again divided by volume, so it is become rho. Okay, and then the increasing rate of heat, dou of this one over dou t, yeah, which is if you look at it, the rate of increased kinetic and internal energy. So the rate, yeah, so if it is the rate, so that should be divided by time. Okay, so here the increased rate of kinetic internal energy, and then this one is per sorry, per volume unit, and then multiply with the control volume, okay, which is the volume between delta x, delta z, and delta y. And then that's equal with E. So E here is actually the conduction, yeah, or we can write it as a Q as well, okay, because this is the conduction, the heat that the conduction at x equal to x, so this area, minus Ex at x plus delta x, which is this one, and then this should be multiplied with the area. Okay, so the area that is perpendicular to the direction of conduction. Okay, so this gonna be the area, or if you look at it, it equal to delta y multiplied with delta z. Yeah. Okay, and then if in the y direction, in this that direction, okay, we also have q y, okay, q in the y direction, and then this should be multiplied with delta x multiplied with delta z. Okay, delta x multiplied with delta z. Okay, and then with the similar approach, we can also get Ez, the input and the output, which is the conduction to the z minus conduction to z plus delta z, multiply with the cross section. Yeah, so if this is the green one, okay, that one, so this gonna be the cross section area. Okay, and after that, this one is from the conduction, and then we also add the convection, sorry, the not the convection, but the G, yeah, or the gravity. Okay, and then multiply with that one, and then again it is in the per volume, so we have to multiply with those volume. Okay, so in the end, if we divide all both sides with delta x, delta y, and delta z, this would become a limit, yeah, with respect to delta y. This is gonna be the limit respect to delta z, and this is also the limit respect to delta x, and then that's become this one. Okay, so here the rate increase of the kinetic energy and internal energy would be equal to the delta of this one, the energy, each of that, and then plus the of V multiplied with G, which is the contribution from the gravity. And if you write it in vector, in the divergent, this is how you write it, using a bold alphabet like this. This actually comprise become with respect to X, Y, and Z. Okay, so this is gonna be the equation of change for non-isothermal system. Okay, so if we added more addition, or maybe just again change the conduction. Sorry, this is not only the conduction but also the energy as general. The energy also, it depends on Q as well. Okay, so the rate increase of energy per unit volume would be equal to the rate of energy addition per unit volume by convective transport. So this is by convective transport, and then the rate energy for heat conduction, and then the work done by the fluid, if any, and then the work done by viscous force, if any, and also the work done by external forces, for example using gravity. Okay, so this is also quite similar, of course, with the heat shell balance, the energy balance as well, and then we rewrite them into equation of change. Okay, you already know also, we can see this one in appendix B to see the for the equation of change. Okay, so the tables that we're gonna revert in the appendix B, the first one is the Fourier's law, appendix B2. So you can see the Cartesian coordinate, the correlation between Q, the heat flux, and the temperature, which is Q equal to minus K dou T dou X, for example, for Qx, and so on. And then where so this one is this is the heat flux, and then with that one you can also revert if you're using cylindrical coordinate. This is the QR minus K dou T dou R, this is Q theta, and also QZ. Okay, and then the last one for spherical coordinate, you can get QR, Q theta, and Q C for this one. Okay, and then the one that you're gonna need actually in appendix B2, okay, which is the explanation of that one. The first one is the Cartesian coordinate, which is the internal forces, the internal energy is actually expanded into rho Cp. Okay, so you can see here that there is rho Cp, and then dou T over dou T, temperature over dou time, and then with the V, temperature of Vx, Vy, and Vz. And then this is dou Qx over dou X. Okay, so this one, where this one is actually if we have a different changing in pressure and temperature, pressure, time, also temperature, and rho, but usually this one is maybe neglected. Okay, and then this one is actually term for dissipation, viscous dissipation. Usually it can be neglected except for system with a very large velocity gradient. Okay, and then this term is actually equal to 0 for fluids with a constant rho. Okay, and then usually in the problems we assume that the rho doesn't change too much with temperature, so we can assume this one equal to 0. Okay, and then with the similar one you can get the cylindrical coordinate, which is rho CP, and then it's quite similar with the previous one with the different coordinate, and also the correlation between RQR, Q Z and Q theta. Okay, and this is also for the spherical coordinate. Okay, so looks like so similar to the momentum. So in the momentum equation, if you remember, there are two type equation, B5 and also B6. The first one is a correlation between velocity and tau, okay, and the second one between the velocity and again the the velocity as well, okay, from the right hand side and also the left hand side. Okay, in similar to this one, for energy equation, you gonna have appendix B8 and B9. The appendix B8 that correlates temperature, yeah, this one, the temperature, with Q. Okay, and then at appendix B9, if you look at here, about temperature correlates also with temperature. Okay, so it's actually it's quite analog with the momentum equation here. So when you want to do the application of this one, you may want to have a look which equation you would like to apply. Is it B8 or B9? Okay, up to here, any question?
Oh, I have a question, Bu.
Yes.
I still couldn't understand the phenomena where like the kinetic energy plus the energy by heat could be the net of conduction. Like, can you explain the phenomena regarding that, Bu?
Which one? This one or this one?
Yes, both, Bu. Because like for me, the equation like it's kind of weird, Bu. Like kinetic energy plus internal energy, then you get because like the model itself isn't moving and stuff, right, Bu? So I'm still confused. Where did the kinetic energy come from?
Yeah, the kinetic because this is okay. So um, in the principles, we can go to the more details. So oops. Okay, so we know that the energy, okay, in here we know there is a velocity, right? Okay, and then so the energy regarding about the velocity that or maybe Vx, yeah, or Vz or something. So the kinetic energy regarding the velocity is called kinetic energy. Okay, and then U is actually internal energy. And internal energy, if you look at it, is similar with the one that you see in thermodynamics. So it's actually I didn't remember the real exact. So it's actual to the enthalpy and equal to mCp delta T, something like that. There should be something with this one. So that's why if you go back to here, it just become rho Cp dou T dou dou temperature dou T. But anyway, let's have a look in the book if they have more explanation. So
Like, Bu,
yeah,
the velocity. What's causing the velocity, Bu?
because okay, I know what you mean. Wait. It is all about the possibility, Kevin. So if you don't have velocity, then you don't have the kinetic energy. Okay, so because we're thinking about a fluid, and then if the fluid is let's say it has a velocity, then it will have energy. But later on, as like you said in the later on in the application, you may want to see later on, is it applicable to your application or not. For example, we only have conduction. Maybe if you are if the fluid doesn't move, for example, it's only because of there's only conduction, maybe this one becoming zero. Okay, so this later on in the application we will see that this would only applicable for a fluids that is moving, and then it will have, for example, some temperature increase because of the difference temperature in here, or because of viscous dissipation, or something like that. Okay, so I think if you want, if I want to ask your question why there is a kinetic energy here, this is just general expressions.
I'm still missing the point, Bu. Is it something like, so there's like a stationary block, then it, like there's a fluid flowing through it. That's why there's velocity, Bu.
Yes, yes, that's why there
Oh,
is a time over here. So if the velocity is changing with time, so that would be a net rate changing. Or if this is not a velocity, if this is not a fluid, this is only just a solid block, let's say, I think we may neglect this one later on, but later on in the application. So at least we just look at the molecular view, and then we look at the the general expression. Let's say there is a fluid over here, it may move to that way, it may move to that way, or it may move to the y direction, let's say, and then what is but actually if it is moving through three direction, I think it's gonna be like swirling. Yeah, I don't know, maybe it's gonna change something. Okay, did you
yeah, it makes more sense, Bu.
yeah,
Thank you very much, Bu.
it is a really general expression. So like we learned in the momentum transfer, or the momentum balance for the equation of change, we also understand that not all of the phenomena are included in here. Okay, so for example, this one, this actually tells you about the energy of those substance in the control volume per unit, per unit volume, and then if you this equal to the kinetic energy and also the internal energy. The correlation, or the contribution of temperature changing is actually going to be in the U, because for the U it would be about rho Cp something, would be rho Cp and delta T or something. Okay, all right, and then not all of this gonna be applied, it's gonna be just depend on the application later. Okay, so here back to here, so this is the equations we're gonna use, application B2 and also B8 and B9. Okay, so application B2 again is about the Fourier heat conduction. If you remember, for momentum it is tau, tau yx, let's say, minus mu del dv y over dx, for example, and then similar to this one is for energy as conduction. Okay, and then this one is the equation energy in the term of Q. So you can see here that there is a Q. If you want to know the temperature difference at temperature distribution, you need to substitute the Fourier's law into this type of equation. And then the last one is for the equation of energy for pure Newtonian fluids with a constant rho and a constant K, or thermal conductivity. Yeah, this one we're gonna use this. Okay, and the value of thermal conductivity, even it is not explained in this lecture, but we usually the scientists or the chemical engineers will measure that in experimental section. Okay, so the field of chemical engineering really blooms around 50s 90s. Yeah, so it is like more than 70 years, so we should be more advanced, but at that time they have generate a lot of data regarding thermal conductivity, so then we can use it, yeah, and then it included in softwares, included in a lot of database. For example, in HYSYS, for example, if you want to find like common liquids, common solids, we can find the property as well. Okay. Okay, and then here I just want to add more about equation, dimensionless equation. I took it from Pak Mobiar's almarhum PowerPoints, yeah, just to emphasize the concept. Later on, we're gonna see, for example, Grashof number. If you remember about uh, the forced convection and also the free convection. Yeah, for the free convection, we use in the application use Grashof number, which is a buoyant force divided by inertial force. So all of them have different units. So when you divide two of them together, they're gonna have dimensionless form. But the quantity will look at will tell you something happens. Yeah, for example, I know you know a lot about Reynolds number. We know that when the Reynolds number is very low, 0.2 or only 2 or up to 2000, we know that the flow is laminar flow, while if we have a Reynolds number with thousands, yeah, or 20,000, that means the viscous force is very slow, very low compared to the initial force, that it would be a turbulent flow, for example. And the Freud number, it is inertial force divided by gravity force, which we usually use Freud number to scale up our calculation from lab scale into maybe semi-pilot or pilot scale or commercial scale. Okay, so now let's have a look about example. Maybe we want to this one, yeah. The I think we can consider the problem in 10.8. Yeah, if you remember about the fluid flow profile fully developed laminar in the tube. So okay, I remember it's gonna be looks like this. So let's say we have a forced convection in a laminar flow in the pipe. Let's say we have a fluid at temperature T1. Okay, so this one is temperature of T1, and then it flow in this direction. Okay, if you remember. And then on the side, yeah, from the outside, you have the heat flux. Yeah, to take it out, maybe using cooling water, or maybe using maybe using cooling water something. But the heat flux is a constant. Okay, the heat flux is constant, is Q0. So the first one, we can find the continuity equation first. I think I can take this one out. Maybe let's copy the formula. Okay, so let's copy the formula from the appendix maybe. Wait, let's copy the equation. Okay, the first one, for me to explain this one, maybe we can write it here. Okay, so we have something like this. Okay, and then maybe we can write the equation first. Can you see it's quite clearly? Is it?
Yes, it's clear.
Okay. So the first one, uh, again, equation of continuity is always used just to make sure about the, if you want to know the correlation of velocity. Okay, so here let's say we can see, because it is cylindrical. Yeah, this is a cylindrical coordinate, so we can use up to there. Okay, so we can see, and then we know that from the formula here, it is let's say very, we have a constant, or it is a steady. For example, we remember, yeah, this is a steady. It has a Newtonian fluid. We have the constant rho, and then also the constant mu and so on. So we can see this one on the cylindrical coordinate. Okay, because it is steady, then this one equal to 0. Okay, and then they only have Vz, yeah, while we don't have Vr, and we don't have also V theta, yeah, because we remember it only flowing into the z direction, so this becomes 0, and this becomes 0 as well, yeah, this one. So we have this here. Okay, so from the equation of continuity, we know that dou over dou x dou z equal to rho v z. Okay, so there is no changing of v to the z, yeah, like that. Okay, so that's why this happens from the continuity equation. We know that this one, that we got it. Okay, and then let's say from the let's now see the second one using equation of continuity. So let's just insert, and I would like to copy using the previous one. Okay, so equation of energy. Okay, again I would like to copy this one again, just to okay, and then now for the equation of energy, it's actually, again, we know that we can use B8 or we can use B9. Which part do you think we can use? This one or that one? B8 or B9?
We're given Q, right? So I think B8. Yeah.
Okay. Anyone would like to have more information or different ideas? Do you agree using B8?
I think I also agree.
Okay, so let's go back again. So we know that this one we have yeah, this one, yeah, we they have a T1 and also a Q, yeah. So yeah, it depends, yeah. So here we have uh, if we know the temperature, we can use the B8, and if we don't have the temperature, we if you have Q, then we can use Q. Okay, so here okay, so but here mm, wait, it might be simplified. Yeah, okay, let's continue that one. So here using we can use B8. Okay. Okay, so here you can see again, because it's cylindrical coordinates, so we're gonna use this one. So then you end up with so for example this is we don't have T, yeah, we don't have T with temperature, we don't have VR, okay, we don't have phi theta, we have phi z, and also we have dt over dou z, yeah, which is the difference of temperature, changing of temperature with the z direction. That would be some changing. Okay, so that would be rho cp and then phi z dou t over dou z. Yeah, this is from the left hand side, and then from here we can see here that a 1 over r dou over dou r of rqr here. Okay, we have this one, and then up to here, and then we don't have dou kz or dou z. We may have this one, yeah, and also we can neglect that one. So that would be minus 1 over r dou over dou r rqr plus dou qz over dou z. Yeah, that one. And after that you can go back to equation of this one, the Fourier's law of conduction, to find what is where is it? Okay, to find what is QR equal what, yeah, and then QZ equal to 1. Okay, so this is one possibility, or the other possibility is just to use the appendix B9. Okay, so if we want to use appendix B9, but again when we want to, for example, to find the equation again later on, let's look at the problem. Yeah, let's look at the available boundary condition. Okay, or so the first one, this is the first approach. Yeah, the first approach, if we use equation of B8 using the Q, let's say if we know the Q. Okay, but again, sometimes the Q is usually comprised of minus k dou t over dou r, for example, or minus k dou t over dou z. Yeah, so sometimes if the boundary condition later on would be in temperature, we can use the appendix B9. Okay, but actually both sides is gonna be okay, as long as because if we add appendix B8 and then we add the Fourier's law, that's gonna be appendix B9. Okay, and then if I can just copy again the appendix B9 over here. Okay, so what happened if, for example, we use appendix B9? Again, using cylindrical coordinate, yeah. This one, let's say steady. This one, there's no VR, there's no phi theta, and then again we have phi z over d dou t over dou z, and this is, we have the function dou t over dou r, and also dou t over dou theta, we don't have that one, and also this one dou theta. So especially this one, and also that one is the same. So if we put k dou t dou r to here, we put the equation for dou t dou z to here, this become this formula as well. Okay, so both sides, that's gonna be okay. But again, let's check. I also forgot what is the problems looks like later on about the boundary condition. Let's have a look. If the boundary condition later on is gonna be in temperature, then we can use this one, or the previous one also similar. Okay, now this one I check it from PowerPoint from Pak Arsa before. So in here Pak Arsa also adding equation of motion if you want to look at the profile of velocity, right? Yeah, we also know the profile velocity from the equation of motion, because the velocity in the center is going to be different with the for example in the sides, for example. Okay, and the energy equation we got similar, of course, from this one. Okay, and then the last one, if you look at here, there is this one. Yeah, if you look at over here, this is called viscous dissipation. Okay, so this called viscous dissipation. If you want to see what is viscous dissipation, you can get appendix A. This term may be neglected except for a system with a very large velocity gradient. Okay, and then sometimes in flowing of the fluid here, the viscous dissipation is neglected. Okay, so there you go. If you compare it with let me stop share and let me share the screen, let's say, and then let's compare it with the one that we get. Oops, sorry, not this one. Okay, let's compare it with the one that we learned last few weeks from the previous slides. For the convection again, yeah. So let me remember. Oh, not this one. Convection, yeah. This one, yeah, it's similar with this one, just different. This is vertical, but this is horizontal, yeah. With the first convection, remember we have the fluid flowing, and then there is a heated up, yeah, coming like that. Okay, and then if you look at here, the resulted yeah, the resulted, okay, see the resulted experiment, the resulted equation is actually similar, yeah. So this is dou v over dou t, yeah, here, I think for the energy equation, the velocity is embedded somewhere here, okay, and then that would be equal to k, yeah, one r dou over dou r, okay, and then here dou t over dou r, and then we neglected this which one, the conduction. Okay, so this part is quite similar. Okay, and then we can see the boundary condition again from this side. Okay, and this one, the viscous dissipation, we're gonna neglect it. Okay, so both sides using the laminar flow, and also using the equation of energy equation, and also using a shell balance, that should be quite similar. Okay, another one is example about tangential flow in an annulus with viscous heat generation. Okay, if you remember about this case, you know, where we have an incompressible fluid, yeah, around this two annulus. Okay, so there is an annulus, and then it is filled with incompressible fluid. The inside cylinder is stationary. The outside cylinder is rotating with angular velocity of omega, for example. Okay, so here we can also use the equation of energy to try to apply to that one. Okay, so here in this tangential flow of annulus with the viscous generation, you have the outer one, yeah, so this is the, let's say, with the temperature T0, and the outside is, let's say, TB. It is an incompressible fluid with constant transport properties, and the outer cylinder rotates. The inner cylinder is steady or just stationary, and then it is a laminar flow, for example, in the theta direction. And then we know that it's going to be one dimension momentum and heat transfer in axial direction, and there is a pressure in radial and axial direction. Okay, to put the energy equation, because it is using cylindrical, okay, so using cylindrical, we can again go back to wait, to here, yeah, to the energy, and then we're gonna use the cylindrical energy, but in the term of temperature, yeah, because we know that it is actually, we have this one in the temperature with the temperature. Okay, appendix B9. So let's have a look. Oops, not this one. Okay, so in the appendix here, then we can see that this is the equation, rho Cp dou T over dou T, temperature over dou time, and then Vr dou T over dou R plus rho V theta over R. Yeah, we know we don't have this one because it is steady. We also don't have Vr. Okay, and then we don't have we have V theta, but we don't have dou theta over dou T over dou theta here. Okay, and then we don't have Vz because the angular only rotates like with rotate with the theta direction. Okay, so it doesn't flow with the R direction or in the Z direction. Okay, so then we can also delete that one, and then this equal to K 1 over R dou dou theta over dou R, and then we don't have the second derivation with d theta over dou theta square, and also dou square theta over dou Z square, also we don't have that one. Okay, so because of that, that's gonna be the energy equation. Okay, that's gonna be the energy equation where we have now it end up with rho yeah, so it would be all equal to 0 here over here and become to that one. Okay, and then for the dissipation function, if you want to check, but yeah, there's some dissipation around here. Yeah, there would be some dissipation. We call it disipasi panas. Yeah, like before, because uh, it is defined by R dou over dou R multiplied with V0 over R square. Okay, remember in the previous case we write dissipation, heat dissipation as a heat generation. Okay, and then but actually if you want to add the dissipation function in appendix A, so let's have a look on appendix A. Wait, is it a space? Dissipation. Wait, dissipation. Yeah, this one, sorry. It's not A, yeah, in appendix B7. Yeah, so this is called B7, just an additional one. So in dissipation function, because when you have the difference in temperature or difference in velocity, you end up with this CV, yeah, or we call it dissipation. So I want to just click on this for the cylindrical coordinate B72. And okay, maybe just copy into here so we can check if our calculation is right. Yeah, so this is the dissipation, yeah, from for quite similar here. Okay, this is for cylindrical coordinate. Wait, looks like I copied the wrong one. The dissipation. Yeah, it should that one. Yeah, that one. Okay, so this actually is gonna be the dissipation that we see. Okay, and then after that we also can get the energy equation. Yeah, this is the energy equation that from appendix B8. Yeah, from the energy equation, and then if you look at here, there would be some V0, V theta, sorry. And for the phi theta, we only can find the correlation phi theta with R is by adding with the momentum balance. Yeah, if you remember, put it into so you have to check with equation for equation of motion. Yeah, equation of motion for phi theta, so you can get the correlation between phi theta and also with the R. Okay, so then if we add all of them together, later on we can get the energy equation. So this gonna be the energy equation with the boundary condition when T equal to TB, R equal to R, and T equal to T0, R equal to KR. So it's basically from the energy equation or from the shell balance, that should conclude similar direction. Okay, and this one is actually quite difficult to check, yeah. So to see what is the formula. So here I got help from Pak Arse here to change the first one. We can change this into a dimensionless equation. So this is a little bit changing, yeah. So basically we want to change here we have a variable of so we have variables t, okay, we have variable of r, okay. So here we change, and also we have variable of the t and r, and then we change it into dimensionless form. Okay, from the birth book they changed the this one, yeah, c up c, yeah, c, this one, this value is actually the dimensionless number for radius. Okay, and then this theta here is actually the dimensionless number for temperature, and then this one another constant or something, yeah, because this is all about the constant to find the constant because mu omega 0 r k, yeah, all of them is a constant. Okay, so then by changing this energy equation into here, then we can get another form of energy equation, dimensionless form, which is with this boundary condition, with when c equal to 1, or when which is t equal to tb, yeah, r equal to r capital R, which is this one equal to 1, and this would be equal to 0 at this value equal to 0. Okay, maybe try you can using in a practice, try to change this one into dimensionless form, or maybe later we can have a separate session to derive how to change the equation into a dimensional form, yeah, because looks like in the exam that would be 1 point also to be asked about changing from equation of energy that you get to the dimensional form. Okay, and then later on when you have the temperature profiles, yeah, in the book, we can actually if you remember in the book they treat the annulus as a parallel plate, yeah, they change can be using as a parallel plate like that. Okay, or changing annulus looks like the annulus like that. Okay, so later on in the birth book you can find that if you treat it using annulus like that, the theta would be this value, while using annulus of parallel plate using this one. I know this is very advanced, but at least we see what is the impact if we actually put it into some numbers, yeah. So here I would like to give you some examples. This is also from the book. Let's say we have the value, for example, let's say we have rotate, the outer one again rotates with some angular velocity, okay, and then this one with the mu, or with the viscosity, for example, with centipoise. This is the raw of the fluids, yeah, it's quite dense, like I think this is larger than water, yeah, water is only 1 gram per milliliter. And then we also have the K, the thermoconductivity of the fluid. We have the temperature, the TB and T0 and also R, and we can see also we know the omega or the angular velocity. Okay, it seems that if the K is 0.99, which is K would be if you remember the, like for example like that, yeah, from the center this is KR and this is R. So if the K is 0.99, so that means you have a very thin layers of a thin very it's very similar, yeah, with the inner diameter and the outer diameter. So you can think that as a plate, like a parallel plate. So what happens here from the energy from here we can actually get the temperature profile by using numerical. Okay, so this is not going to be explained in here, but if you're using numerical using finite different element difference, yeah, we're not gonna do that. I got it from Pak Arse, yeah, to explain that one. But actually, if you look at here, when it is quite similar, yeah, when K is 0.99. Okay, so the calculation this tells you about T minus T0 divided by TB minus T0. Okay, and while this C here equal to R equal to R. Okay, so if you look at here the temperature, this tell you about the temperature profiles. Okay, the temperature profile, how much the temperature is changing with the reference to T0 or divided by the initial one. Okay, so from R equal to where the horizontal one tells you about R over capital R. So here both of them is dimensionless dimensionless unit. This is the dimensionless unit for temperature. This is dimensionless unit for radius. You can see the profiles. Okay, so you can see the profiles. So even you use a plate like two parallel plate or using annulus, that would be quite similar. So this tells you that the model can predict the temperature profiles inside the fluids between two cylinders. Yeah, you know the temperature profile inside the annulus. Okay, and then Pak Arse also add some more explanation. What happened if he changed the K? Okay, the K become 0.5. So let's say they have this very large cylinder, and then they have the inner one cylinder, for example, where this is gonna be the KR, and then this is gonna be the R, where the K is only 0.5. So you can see that this is there's so much difference between the R, the K, the inner cylinder KR, and the larger R, and I think it's not gonna be good if we put it into a parallel plate. Yeah, of course it's not gonna be good because this doesn't look parallel. So okay, so and then Pak Arse also do the calculation by using finite difference elements, yeah, to get the profiles. And then yeah, it actually looks like what we predict. So if it is in a low K, yeah, which is that means when so 0.5, so equal to 0.5 R divided by R, yeah, where the K is 0.5. You see that from here to here it has a difference predictable, yeah, difference profile. This one is using annulus. If you use the annulus equation, okay, and this one if you use the plate equation. Okay, so here the two equation, the first one that we use using the annulus, yeah, which is we got it from this equation, the energy equation, because using cylinder and then we treat it as an annulus. And this one we got it from the previous one, the shell energy balance, yeah, where we treat the annulus like a parallel plate. Remember few weeks before. Okay, so then we can see here that different equation, yeah, different equation with a different assumption, it will result in different prediction. Okay, but the prediction sometimes, of course, because this is modeling and we predict, the prediction can be good, it can be we can still assume quite similar, for example. Yeah, it gonna be depends. Okay, anyone? So I think I just show additional here. Of course, you're not supposed to, you're not ought to derive this up to do the calculation up to here, yeah. The students in the master level, they will ask to do this using Flex PDA. Next week, Pak Anggit will also explain more about Flex PDA as well. But the remember, I think the lesson that we see is actually we can use the equation of change for energy, the incompressible fluid, with what different application, and then you almost we can't actually get the profiles like momentum, yeah. It's very different. Okay, and maybe one more I would like to also explain to you about the one that we see from where is it, from the other PDF that I give to you. So let me just see again, where is it? Okay, I got it, this one from I also was still learning when I came here to ITB few years ago with Pak Amubiarya almarhum. So he was a senior lecturer, he was a professor in chemical engineering, and I think he spent most of his time studying transfer phenomena, and he passed away around 2017, I think, and then and before that he gave all the materials to me, yeah, to just to check. Okay, I just want to show you. So this is quite similar, quite energy. So I want to show you this one. So in so later on, you may want to see, maybe you can see, maybe you see some of this in heat transfer, maybe, yeah, in operasi perpindahan kalor, something like that. So to find the profile, for example, between if we want to heat a slab means like a block, yeah, balok, yeah, like if it is a slab, and for example we know this is the center of the slab, and then this is the surface of the slab, and it has some temperature. For example, the surface has a high temperature like that, for example 0, so that means that this is actual to T0, yeah, which is the 0, and then this the inner temperature still very low. Let's say this is the inner temperature is still 0, for example. So 0 means still T0, well here is in T1, let's say. So here is actually this gonna tells you about so from all the equation, like the equation energy, then we actually plot it into a graph. Okay, and then we plot it into a graph, and then this is a typical graph for heating slab. So for example, if I want to, but because the good things that we want to learn is what is the profile of the temperature in the middle, for example, then we can see, for example, this is the center of the slab, this is the surface of the slab. So for example, at the middle like that, and after that we can see this one, alpha t divided by b squared. So alpha is called heat diffusivity, yeah, or equal to rho. Can I write something here? Oh no. Okay, can't write something here. So alpha is actually, maybe I can write it somewhere. Yeah, maybe I can write it here. So alpha is actually rho k cpk. So it's actually the thermal diffusivity. Yeah, the thermal diffusivity. And then if you, oops, yeah, the thermal diffusivity. So again, at least if you know the thermal diffusivity, you know the time, you know the b square, or the length of that one, you know how can you get the can the heating the slab. Okay, this is also similar, for example, about how to heating a cylinder. Again, T minus T0 divided by T1 minus T0. So if you want to know the profile temperature within the radius, and also the temperature, and also the time, so you can see this is gonna be the profiles. Okay, so this is again just one examples or application of energy, the equation of energy, yeah, using the application, and then we can get this type of drawing. We can use also a flex PDE, yeah, if you uh, for some equation, because it is defined already, we can put it here like a graph like that, but we can also make this graph using flex PDE. All right, I think that would be conclude the discussion, yeah, about the energy. So I want to go back share screen, this one. Okay, so again back to here, I just give an example for again the tangential flow, and also for the this one, yeah, the first laminar convection in laminar flows. All right, if you have any questions, you can actually ask question while I'm checking. Maybe just we still have some time, so I think we can get some example, yeah. So let me check. Do we have some examples from last week's? Okay, any questions? No? If not, I would like to share maybe an example in this one. Maybe you want to try? So maybe let's try this one. I can copy them to PPT, so I can yeah, write something, yeah, here. Okay, I think what can you do? You may want to just have a look, yeah, maybe studying about 10 minutes about this one. This is an example from 2019, I think. Uh, Maybe, and then try to sketch the formula, and try to sketch the phenomena, and then using a quotient of energy, find the differential equation. Okay, let's wait for 10 minutes. Yeah, I will wait for 10 minutes for you to try it. And then don't forget to see using appendix B to use the equation of energy. Okay, anyone? Have you tried? Or maybe who want to volunteer to write the schematic? So again, if you look at here, you see that where's my pen? Okay. At least you see, yeah, sorry, this is still in Indonesian, but we can see the maybe some clue, yeah, here. So it is, we have a vertical, sorry, this in inclined plate, plat sejajar miring. Okay, this one. And then we have a Newtonian fluid which is stationary, ya, diam tidak mengalir. So this also one of the clue. Okay, so this is, and also this one. Okay, and then the distance between the two plates is B. Okay, the temperature on the top is TA, and the bottom one is TB, where TA less than TB. Okay, so and then we have also the physical properties, the density, the conductivity, and so on, and then maybe find the sketch. Okay. Okay, who want to try this one? Right. Christian, maybe? Do you want to try?
I'm not. I'm not sure, man.
Really? Just try to sketch it. Uh, right. Or maybe uh, show me what to do, and I will write it for you. What should I write then? What should I sketch?
Okay. Wait a minute, man. I'll try to give. I'll try to make a good. Okay. So, I think between between two the two plates that are actually meeting. What is meeting in English?
Incline.
Yeah,
Okay,
there's like two inclined planes.
like that. Okay.
And then so actually so in the middle the fluid is actually flowing between the plates.
See,
So
this is diam. So it is stationary. So it just stay there. Okay.
yeah, no man, I mean like so the fluid is actually there between the plates, but it's actually not moving.
Yeah. Okay. And then so what else that we can see? How about the zero coordinate, titik nol koordinat ruang? Where should
I
you
think
put it?
for me I put it on the edge of the two, on the edge of the two plates on the left hand side.
This one?
Yeah.
Okay. So what is this direction?
Z
Yep. How about that one?
R.
Is it a radius? Is it a cylindrical or is it Cartesian?
Wait. Oh yeah. Yeah.
It's a plate. So
Oh, what X? Y.
yeah, X. Okay. Okay. Thank you, Christian. Gamma, maybe you want to add again a boundary condition that you can see here.
Um, I'm not exactly sure. I'm guessing that. No, I'm not sure, ma'am.
This is my clue. So you have this one and you have that one. So where should I put all this clue?
Oh wait. I'm still not sure, ma'am.
Yes, this is said that temperatur plat pada posisi lebih atas adalah TA. So the temperature of the plate on the upper position is TA. So you can say, okay, this is a plate, okay, and this is the in this plate it has a temperature of TA. Just simple as that, okay. And then the temperature at the lower one is TB. So you can maybe write, okay, on the lower plate it is called TB. Or if you want to make sure that it's written right, yeah, you can say it. So at the lower plate, it is at what position? This is
I think I want to try to.
yeah. In
So
what?
So I think the boundary conditions is at z equals to 0, t equals to tb.
Nope, not z equal to 0 in that side. So it would be at.
Oh, sorry. If x equals to 0.
Okay. So gamma Christian. So you can see this is at x.
X equals to 0. T equals to tb.
Okay.
And at x equals to b, t equals to ta.
Okay. Okay, good. So you got everything done. Okay. As you see, this is syarat lulus ya. So you have to up to here usually. Okay. Right. Thank you for being with me, and then let's see the next question. Okay, the next question, using the equation of energy, find the differential equation that shows the temperature profile in a steady state and also the boundary condition. You get the boundary condition here, right? Okay, so you got it already. And then we want to see the table of equation of energy. So what I would like to see, go back to the equation of energy there. There are table B8 and also there are table B9. What do you think we need to get? Maybe Alisa would like to help?
I think the B9, because on the problem it states that we have constant P and K.
Okay, so let's copy this B9, and looks like we just gonna use this Cartesian coordinate, yeah. So I can maybe copy here and then maybe just crop only the Cartesian coordinate. Okay, so this is the equation of energy. Okay, the clue is fluid is stationary, fluidanya diam. Yeah, so that means we don't have, do we have Vx? Yeah, do we have Vy? Do we have Vz? Okay, so that's as simple as that. Okay, so look at the clue on the again on the here, yeah. So it's about 30 minutes here. Is it diam, yeah? That one. Okay, the second clue is here there is a constant of with temperature, so we have to check as temperature with time, yeah. So we have to check is it steady or unsteady. So if we look at here, it is steady, yeah. Tunak, yeah. Tunak means steady here. So because of it is steady, so that means dou T over dou T equal to 0. So by having that one, we can see, and also if you look at the sketch, the TA and TB is only in the X direction, yeah. This is V and Y, okay. So here we have rho Cp dou T over dou T, yeah, which is the the unsteady one is actually steady, so we can make it 0. We don't have Vx, we don't have Vy, we don't have Vz, so equals again all equal to 0. And then this is equal to k. This is dou square t over dou x square. So do we have this one, a changing of temperature in the x direction?
Yes, we have.
Yeah, we have. Okay, good. So we have this one. Do we have a changing temperature in the y direction?
We don't have.
No. Do we have a changing of temperature in the z direction?
No.
No, yeah. If you have a flowing fluid, maybe in that way, maybe we have a changing of z in the z direction. But here, because the fluid is stationary, okay. So this one is that one, and then this one is viscous dissipation. Yeah, this one also can be neglected because we don't have a change in velocity, yeah, too much. Okay, so then this actually we can conclude that this equal to 0 equal to k dou square t over dou x square. Okay, so that this gonna be the equation. And the boundary condition like you write before, so thanks to you all that this is gonna be the boundary condition, which is t equal to tb, and then x equal to b, t equal to ta. Okay, and then maybe we can go back there. So and then turunkan persamaan. Okay, so we have to find the temperature profiles, show the temperature profiles. Maybe we can just, the next steps, we can just okay, maybe we can just write, so dou square t over dou x square equal to 0. So do the first integration, dou t over dou x equal to c1, and the second integration, t equal to c1x plus c2. Okay, and then we can add your boundary condition here. Okay, to the equation. For example, just forget, when x equal to 0, t equal to tb. When x equal to 0, so this is 0, t equal to tb. When x equal to b, t equal to ta. So c1b plus c2 and this one, tb, yeah. So this one, so we know that c2 is equal to tb. Okay, and then we can substitute. So what is c1? So c1 is ta minus tb divided by b. Okay, so we know the c1, we know the c2. So by adding 1 and 2 to the equation, so we get t equal to ta minus tb divided by b multiply with x plus tb. I think this is, yeah, this is actually we know already, yeah, rather than by deriving the equation we actually know, maybe we know already. Okay, but so this is gonna be the temperature profile, but so if you got it right, that is okay. But sometimes we like to write the temperature in difference. Okay, so with the reference, so we can write it at t minus tb equal to ta minus tb divided by x over b. Yeah, so we change this b into here, or because this is also the constant related to temperature, we can divide them with that one. So t minus tb divided by ta minus tb, that one at x equal to b. So that can be the equation as well. Okay, so this one is okay, this one is okay. I think that's why people likes to write using dimensionless. Yeah, so just if I have additional questions, do you want to make a dimensionless? So maybe we can make dimensionless, for example, using theta, for example, as t minus tb divided by ta minus tb, for example. Or maybe change I don't know what is x and b. For example, I don't know, maybe this one dimensionless. Yeah, maybe you want to find the dimensionless for area as well, for example, x divided by b. Yeah, maybe you want to find this is also distance, this is also distance, so distance by distance become a dimensionless. Okay, but this one is okay, this one is okay. Okay, and then the last one, oh, it is almost 11. And then find the equation that shows the temperature average. Yeah, and for the temperature average, is actually you can go back to I think in the momentum transfer something. So the average temperature is defined as the temperature here, and then you need to integral, yeah, to do the integration respect to the z and also the x. Okay, so it maybe looks like the integral of t to the x from 0 to b, and then integral as well to let's say to what is the length? It doesn't length. Yeah, let's say the length is w for l, for example, from z from 0 to l, so to the length. Okay, and then you can substitute and then and this is divided by again from b to dx, and then from l to dz. Okay, so then you can get the what is called the temperature. Yeah, so this is the temperature. Change that. So let's say this is number 3. So let's substitute the 3. So this is 0L and 0B to T equal to TA minus TB divided by 2 multiply with X. Per B, yeah, per B multiply with X plus TB dx dz divided by that one. Okay, so you may want to first do the integration from here to here first. Okay, and then when you get the result, you want to do the integration with that one. Yeah, and then divide with integration to dx and also integration to dz. Yeah, okay, try it. The result I tried before, the result would be the average would be half of TA minus TB, I think. Yeah, this is that I tried before, so yeah, maybe you can try it. Okay, so again, so this is maybe a typical questions. At least you know what to expect. Yeah, again, similar, you have to sketch the graph, you have to find the boundary condition, you have to write the equation and then try to solve it. And like I know, of course, the mathematical is gonna be a bit tricky maybe. Yeah, but yeah, let's see. And then if we have some time next week, I can also give you some more examples, the equation of change, for example, for the end steady state. Yeah, that would be good. Alright, everyone, it's 11 ready, so thank you for your attention, and then have a good weekend, and then I'll see you again next week.